In this video, we're going to go over the idea of secant of a circle on the Euclidean plane. So what is a secant? A secant of a circle is a line that contains exactly 2 points of the circle. The following figure is a typical example of a secant. So in this figure, the line intersects the circle at precisely 2 points, point A and point B. In comparison to other configurations, we will have tangent to a circle, which is a line that intersects the circle at precisely 1 point. Another possibility is there is no intersection between the line and the circle at all. Let's look at the following exercise. Suppose that lines L and N are secants to the circle, as in the figure, and they are parallel. What we're going to do is going to show that the line segment AC, which is this line segment here, is congruent to the line segment BD. Also, we're going to show that the line segment AD is congruent to the line segment BC. To prove these two relations, we would love to make use of some properties that we have discussed recently for circles and angles, such as the inscribed angle theorem, or the property of the alternate interior angle formed by two parallel lines, as the lines that is given in our figure over here, the line L and the line N. So let's try to explore this problem a little bit. A typical approach in proving a mathematical result is a little bit like the process of reverse engineering. As opposed to begin with a given condition and do the deduction from the scratch, what we would usually do, or what we would frequently do, is look at the results that we want to prove and try to reverse the process by finding some equivalence conditions to the result up to a point at which we could prove the equivalence conditions. For instance, in our problem over here, let's look at the first results that we want to prove. We would love to show that the line segment AC is congruent to the line segment BD. And we recall that, well, these two line segments are chords in this circle. And we have shown that two chords in a circle are congruent to each other if and only if the measure of the intercepted arcs are equal to each other. Hence, what we will need to show is the arc. For instance, let's denote the arc intercepted by the chord AC as arc APC, and the arc intercepted by the chord BD as BQD. So for our purpose, if we're able to show that the measures of these two arcs are equal to each other, then the congruence of those two line segments would follow. On the other hand, we also recall that the measure of the arcs are corresponding to the measure of the inscribed angle facing those two arcs. Therefore, now we observe that the question could be translated to showing the angle ADC, which is this angle over here, is congruent to the angle DAB, because those two angles are facing the arc APC and the arc BQD respectively. So if we're able to show those two angles are congruent to each other, then those two arcs will have to have the same measure which leads to the congruence of the line segment AC and BD respectively. So that would be the strategy that we're going to be taking upon. Now, let's try to look at the simple proof over here for part A. In fact, the major observation is the line L and N are parallel to each other. So we conclude that the angle BAD is congruent to the angle ADC, as they are precisely the alternate interior angles formed by those two lines and the transverse AD. So they are congruent as alternate interior angles. Consequently, the measure of the arc APC, which is equal to the double of the measure of the angle ADC, would have to equal the double of the measure of the angle BAD, which in turn equal to the measure of the arc BQD. Hence, by the property of the relations between chords and the intersecting arcs, as we have discussed recently, we conclude that the line segment, which is the chord AD, is congruent to the line segment BD. So that's how we prove part A of this problem. And for the sake of future reference, let's mark those two line segments to be congruent to each other. All right, so what we're going to do is going to be considering part 2 of this problem. So let's recall that we also like to show that the line segment AD is congruent to the line segment BC. Well, the way to show this problem is to establish some congruence between triangles. Specifically, even from the figure, it's relatively easy to observe that the triangle ACB is congruent to the triangle BDA. So if we're able to establish the congruence relation between those two triangles, then the congruence of those two line segments AD and BC would follow immediately. So let's try to consider how we are supposed to show those two triangles are congruent. Specifically, we already have established the congruence of one pair of corresponding sides, which are AC and BD. Now, let's also observe that the angle ACB and the angle BDA are congruent to each other. Why? Because both of them are intercepting the arc, which is this arc over here. And for the sake of convenience, we're going to pick a point on this arc and denote this arc as ARB. Hence, we have one more pair of corresponding angles that are congruent to each other. If we're able to figure out one more angles that are one more pair of angles that are congruent to each other, then we could make use of the angle-angle side condition to establish the desired congruence of triangle. And it's easy to see that the second pair of congruence angles are given by the angle ABC and the angle BAD. So let's try to think about why that is the case. The reason being is because, you see, those two angles are inscribed angle of the circle, and they turn out to be intercepting congruent arcs, which are APC and BQD, as we have observed. Hence, they will have to be congruence angles. All right, so now let's try to write this scheme down in our formal proof down there. So the key observation, observe that the measure of the angle ACB is equal to 1/2 the measure of the arc ARB, which is equal to the measure of the angle BDA. Since both of those two inscribed angles of the circle are intercepting the same arc. And on the other hand, we observe that the measure of the angle BAD is equals to 1/2 the measure of the arc BQD, which was shown to be equal to the measure of the arc APC, as we have seen in part A up there. And the arc APC is facing the angle ABC. And lastly, we have the result from part 1, namely, the line segment AC is congruent to the line segments BD. Hence, by the angle-angle side condition, we have the congruence between the triangle ABC and the triangle BAD. Consequently, we have the corresponding side AD and BC being congruent to each other. And that is the proof that we want to complete.